Okay, start the report.
Okay.
Honorable judges and fellow competitors, I'm the leader of team of Lafayette and Chen Xinwei. I would like to report problem number 15, boycott effect. So this is the problem statement. If particles are suspended in a liquid that has a lower density than the particle will settle to the bottom of the container. The rate of settling can be affected by tilting the angles that holds the liquid. Explain this phenomenon and investigate the effect of relevant parameters. We think that there are three key questions. What is boycott effect? How does boycott effect form? What parameters affect boycott effect? So this is the presentation outline. We'll talk about experimental setup, characteristics of boycott effect, PNK theory, a further explanation, and relevant parameters. Finally, we'll present our experimental result, which is the tilted angle, viscosity, and the boundary, following with the related theory to our experiment. So here's our experimental setup. In the left picture shows our camera setup, and in the right picture shows our accurate vessel container. Well, we use particle silica sand, about 80 to 120 mesh throughout the experiment. Also, we use liquid or glacial mixture. Here's our experimental method. We track the bottom facing layer sediment by using tracker to track the luminosity shown in here. So since the background is black and the sediment of silica sand is white, the luminosity represents the settling rate of the this settling rate. We also use PITLab to track the velocity field. So here's the phenomenon demonstration. As you can see in the video, the tilted one has a faster settling rate. So we observed the enhancement of settling, and we also observed enhancement of individual particles' velocity. Throughout the presentation, there are some common terminology. We'll talk about the upper facing layer of clear fluid layer, which contains no sediments. Also, there is the top layer, which is often not clear, but it descends, which represents the settling rate. So here's the phenomenon explanation, which is PNK theory. PNK theory is developed to describe the settling rate of tilted settling rate. So ST is defined as the settling of the volume, shown the particle settling volume, and it is equal to the individual particle velocity times the affected settling area. Then we arrange it as shown here. Then we then write ST as the derivative of the height times B times cosecant alpha, and divide cosecant alpha, and we got this differential equation. We now solve the differential equation and get the following form. Previous studies have shown that PNK theory predicts settling rate accurately when Reynolds number approaches infinity, and lambda, the ratio of GR and the Reynolds number approaches infinity. PNK theory also is also right when individual particles' speed stays the same, and this assumption is already contradict to our observation. So here's our Thule observation. We have already confirmed the enhancement of sedimentation settling rate, and from observing the velocity field, we found that the upper facing layer tends to rise up and the bottom facing layer descends. We also observed sideways velocity, which is not caused by gravitational forces. This is another video which is tilted. as you can see, the thin clear fluid layer has high fluid flow velocity, so it drags up some suspension upward, and we refer this phenomenon as instability. Also, we now demonstrate our last observation, which is the larger the tilted angle is, the thicker the clear fluid layer. So this is the last observation. So we compared PNK theory with our observation. So the first three observation is not explained by PNK, and instability is also not concerned in PNK. So we now explain the convection by solving Navier-Stokes equation, and we get the following equation. Note that the middle term, which is lambda times 1 minus phi times the gravitational constant, is the buoyancy force. We note that phi is divided as the local particle volume divided by the particle volume fraction. Notice at the clear fluid layer, the phi equals 0, which exert a upper buoyancy force, and at the closed packet area, phi approaches infinity, which exert a downward force. This causes convection. Also, because of fluid continuity, the clear fluid layer has to be replenished. Water seeps into clear fluid layer, only the component parallel to the walls of the vessel provides drags to the particle. We now use a syringe setup to verify the sideway velocity of the water seepage. This is the ink experiment. So here's the ink. So the ink goes to three phases: drift to the left, push downward, then brought upward, which verifies our velocity field. We now explain the instability. Thin fluid layer with large upward velocity creates large velocity gradient, which result in pulling the suspension layer upward along with it. And then the sediment will rise. We now given our hypothesis that is the larger the tilted angle is, the thicker the clear fluid layer, and result in more stable. And vice versa, the smaller angle is implies that the larger the instability. So we now talk about we now experiment with some parameters. So according to Stokes-Thelen speed, which is affected, we tried the viscosity, which also affects the density. Here's the Stokes-Thelen speed, and we now in some reference of Richardson and Zaki, the individual particle speed can be written as the Stokes-Thelen speed times 1 minus c to the 5th power, where c is experimentally determined. And we also tested tilted angle, which determines the characteristic of clear fluid layer. And finally, we'll test the roughness of upper wall. So here's our experimental result. For testing the vertical sedimentation, we plotted the individual particle velocity as shown here, and we compared it with experimental data. We found that it fits quite well. And next, we will investigate the tilted angle. So this is the vertical tilted one, and when we tilt it with an angle, it significantly affects the settling rate. We now zoom into the luminosity between 0.2 and 0 and found some peaks around here, which is 20 degrees and 30 degrees. This is mainly of the effect of instability. Now we tested some tilted angle. As in the video showed, the more the tilted angle is, it generates thicker clear fluid layer, result in smaller instability, and thus affect the settling rate. We also tested the viscosity. We tilted the container at 10 degrees and plotted the settling rate of the water and 35% glycerol, as shown here. We then, due to the fact that the individual particle velocity is proportional to the difference of density divided by the viscosity, we then implies that time is proportional to individual particle velocity. We then scaled the time by the individual particle velocity of mixture divided by the water, and after scaling, we compared 10 degrees, 20 degrees, and 30 degrees, and we found that viscosity does not affect boycott effect much. Here is the result of the upper basin, the roughness of upper basin wall, and we found that the roughness of upper basin wall do really affect the phenomena. When you tilt at 20 degrees, due to the fact that the upper basin wall is rough and reduces the flow velocity, then reduces the instability. We now come to our conclusion. What caused boycott effect? Boycott effect is caused by convection and increase in affected settling area. Convection and sideways seepage of water cause the velocity of individual particles to increase. What parameters affect boycott effect? Instability decreases the settling rate. Settling rate increase with tilted angle. Smaller tilted angle result in thinner, clear fluid layer, which cause stronger instability. Viscosity does not affect the rate of settling substantially. By making an upper layer rough, we can significantly decrease the settling rate for small tilted angle.
Nice stuff.
There's some reference. Thank you.
Alright, well, juries, I'm the opponent from team Mingdao Mei An. And so now I have some clarification points to make.
Yes.
Okay, so first of all, what is your chosen particle and why did you choose the particle?
We chose to track the luminosity of the bottom facing wall, which represents the descending rate.
The type of the particles that you chose.
Oh, you mean the silica sand?
Yeah.
Yeah, we choose silica sand because it is white, and we can track the luminosity to represent the settling rate.
Oh, so their mass is basically, and the sizes are basically the same.
Yes.
Similar.
About
Like
80 to 120
Wow,
mass.
that's a really small number.
Yeah.
Okay. Then I have another question. So what is the optimal angle of sedimentation time in your experiment? Can you just state the value, please?
Can you just say the pages? Which page?
I sort of lost the track of the page number. Just the experiment result that you had. Okay, never mind. Yes, the optimal tilting angle for the fastest sedimentation speed. Okay, never mind. We'll probably discuss that later. And can you please go to page 10? There is a V0 when you're discussing about the PNK theory. So the V0 on top, is that the initial velocity?
No, V0 represents individual particle velocity.
Okay, so is that the initial or the terminal? Or does it remain the same velocity?
It remains the same.
Okay, thank you. So basically predict that you use another correction method, which is 1 minus c and to the fifth power.
Oh, yes.
Yes.
Which is,
do you think this value really really affect that much, as the value is expected to be very, very small?
I think that's the
okay, I think we'll probably
the result of
later.
Zaki. Yeah.
Okay, sure. So hello everyone, I'm the opponent from Mingdao Mei M. And now I will be opposing the problem boycott effect. Okay, so brief summary of the reporter. The theory that he uses are PNK theory, and he then uses Reynolds number and Grashof number to correct the insufficiency of PNK theory. For experiment setup, they use acrylic vessel, camera light, and silicon sand. For the parameters that they chose to change were tilting angle, viscosity, and the material on the upper layer of the entire basin. For data, they use checker to check the data. More specifically, they check the luminosity. So some advantages for the reporter. First of all, overall clear throughout thought out presentation. So suggestions would be that, first of all, PNK theory is insufficient, which they use their correction method. Second, the definition of clear fluid layer is unclear, I believe. And also the definition of the stopping point where they recorded their data was also not defined as clear as possible. Thirdly, the terms in the equation are not defined thoroughly. Finally, time management can be improved as well. So for setup, some advantages will be that, first of all, clear setup and demonstration footage, of course, and then he also has a very detailed footage with labels on it. Some suggestions will be that, first of all, the diameter of the particle chosen can be different, meaning that there has to be a range, and which they did provide. However, that range is very hard to control, as it is at a very small amount of meshes, which is around 80 to 120, which is basically impossible to occur in real life, in my opinion. And secondly, the size of the particles did not state how to determine. For theory part, an advantage would be that he has a clear theory derivation. However, some suggestions would be that first, he did not show the calculation of the Reynolds number, and secondly, failed to quantify the suspension layer definition in terms of volume fraction. Experimental data, and first of all, the advantage is that he has a clear data, and every chart are correctly labeled. Suggestions would be that they did not show how the sideways syringe experiment is conducted. And they didn't really actually control the initial velocity given by the syringe to the particles, which is a very big sort of like an error in their experiment. So this is going to be my discussion structure because I haven't really made all my clarification points, so I will be making that first. And then I will be asking questions regarding setup and experiment, and then finally I'll discuss the additional parameters that might affect the result. And that's it. I'd like to start the discussion. Thank you.
Let me clarify something first. So
okay.
We denied that, we said that P&K theory is not right because of individual particle speed stays constant.
Yeah, because to my understanding, so correct me if I'm wrong. So P&K theory is calculating an individual particle. So it's basically not considering clotting and collision effect. So it's basically calculating, viewing every particle as an individual particle, right? So that's why you need to have Reynolds number and Gresham number to correct it, because of the instability, right?
I believe that these corrections are made, previous studies have shown that these two numbers, which Reynolds number approaches 0 and lambda approaches infinity, will P&K theory predicts the settling speed accurately.
Okay. Also, do you know why when applying these two, this will make P&K valid?
So basically.
Okay. So let me explain it to you. So yes. So correct me if I'm wrong. I'm just making sure that the clarification is clear enough. So basically what P&K suggests is that every single particle is viewed as individually descending without collision and also without colliding each other and clotting, right?
Yes.
Is that, yes, okay. And the reason behind that is because when collision are happening, right? When collision are happening, this basically slows the entire velocity down. By slowing the velocity down, P&K theory doesn't apply anymore, right?
Yes.
Yes. Okay. So that's why you have to you have to include Reynolds number, and Reynolds number here is calculating the viscosity, the relationship between the viscosity and also the particle. So basically, it's calculating the fact that how particles will be colliding into each other. Am I correct?
I believe that I'm demonstrating here is the observation and why P&K theory is wrong because. The enhancement of of individual particle are velocity and convection and sideways velocity, also instability.
Okay. What do you mean by instability?
So instability here. Wait. No. Instability here. Okay, here. So as you can see, let me draw please.
Okay, sure.
So I tilted the container with an angle, yes. And there exists some thin fluid, clear fluid layer, right. And due to the replenish of water, so it will go like this, and this is high velocity. This flow has high velocity, yes. So it drags some particles upward.
Yes.
So I believe that I set it here, and so what I mean instability is the clear fluid flow drags particle upwards.
Yeah.
That's my instability.
So if it drags it upward, then are you implying that the particle's velocity differs? Are you implying that the particle's velocity different because as you're saying that particles travel through this layer, right? Is it?
No.
Is it correct?
No.
Yes.
So the flow goes here, and it drags some particles upward. Okay. So.
Oh, okay. So you're basically telling that some particles will not be actually descending. Instead, it will be dragged up by the current side. Okay, thank you. Okay, so now I would like to move on to my questions. So first of all, I would like you to define where to stop recording the data. So what is the stopping point? So are you making sure that every single particle is all descended down to the bottom? Is that where you stop recording your data?
So to the experiment. To the experimental part. Here. So after a long time, the luminosity decreases to 0. So I believe that I record the, so I have a Python program which shows the luminosity versus time, and then when time goes on, I simply just observe the luminosity goes to 0, then I stop recording.
Okay, so would you like to describe why there is this error, or is this because of the stability that you just mentioned?
So this theoretical line is the Stokes-Thelen speed times the correction term.
Yes.
And this is called the deviation of theoretical line and experimental data is caused by a variety of parameters, which may be instability, convection, sideways seepage. Yes.
Sideways seepage?
Yes. We verified it with using the ink experiment. So you mentioned that. So I basically inject the ink here, and then I observe this kind of motion. So if I inject the ink with a velocity v, then in this direction,
yes,
it won't be. So it basically turned this direction.
Okay.
So I think that this direction velocity is not so important.
So you say the particle basically.
Yeah, I'm just proving that there exists horizontal. There exists the sideways velocity.
Okay. So this also happens in the other direction as well.
This direction?
Yes.
No, because so the sediment settles down like this. It pushes the water upward, creating a flow.
Okay. Then speaking of the needle part, so when you basically inject all the particles inside it, did you consider the amount of force you applied to the syringe while?
I just said that initial velocity or maybe initial acceleration is not important because I'm using ink to demonstrate that there exists the sideways speed. I'm just demonstrating that, which is not included in P and K.
So are you saying that when you first inject all of the particles inside it, will the velocity equals the velocity it takes for them to descend?
I'm just demonstrating that there exists a flow in this
direction. Yes, because in my own opinion, I believe that so let's say you're slowly injecting it, because that's something I believe you didn't consider, you didn't control, right? So if you're injecting the entire,
I'm injecting ink, not particle. So
also you're injecting you're injecting ink, and
yes.
What does that ink do?
This ink creates a streamline which verifies the velocity field.
Oh, so that's how you start the experiment. Then so at the beginning of your experiment, do all the particles descend at the bottom, and then you start injecting the ink?
No. So first, I simply.
Can you show me, can you just demonstrate how you start at the beginning?
Yeah.
Okay.
So I put this. So this particle are affected by the force more than the ink. So as I started, I put a syringe here, which has so the particle is, I put it here. Then for small time, I change the angle.
Okay.
I tilted the angle. And then
Is this time being controlled?
I inject in. Yeah.
Okay. Okay.
This time is so short that I think we can ignore.
Okay, so you're basically ignoring the time. Okay. I'd like to move on to my next question. So how did you change the roughness of the upper facing wall?
Here I'm just demonstrating that the roughness of the wall, which reduces the clear fluid layer flow speed, and thus significantly reduce the instability. So here, so the instability here, it reduces.
So you haven't answered my question. How did you change the roughness of the upper wall? Is that something that you could change, or is that something in your simulation?
Here is
Yes.
the rough
What
wall.
step?
I changed the wall rough like this, just like this.
So you basically redo the entire upper basin.
Yes. So as you can see here, there's a this.
So basically,
this
split
corresponds with
it into the two, or how
Okay,
do you
thanks for-
change? Okay. So after the 10-minute discussion, we reached a consensus. I believe that first of all, throughout their experiment, there has been a common error, which has to do with the injection of the ink, because the time isn't being considered, and also the time of the tilting between the one angle to another isn't also considered as well. I believe that, however, for their theory part, they mentioned about the P&K theory. I believe that it is good for them to include the correction which they did. So that is a plus for them, since P&K theory, as what I just demonstrated, it didn't consider the clotting and the collision effect that will happen in real life, which is not something that that can be considered in theory. So that's something that we both discussed and reached a consensus on the correction part of the P&K theory, making the entire experiment more wholesome. Thank you.
Okay. Now, the viewer has a similar
Okay, so for the reporter and opponent, so please give a few words you think that mainly cause vertical effect.
What?
Please give me a few words that you think that mainly cause vertical effect.
I think I present three parameters, which is viscosity, which also affects density, the roughness of upper wall, and then the tilted angle.
I think I didn't explain why the phenomenon happens, so I think the main reason for it is basically global convection in simple words.
And do you think that viscosity is the main cause that the vertical effect?
I don't think so. It has to do with viscosity. Of course, viscosity is one parameter, but it is not what makes the phenomenon happens.
Oh, okay. So do you think that when we change the liquid, the viscosity doesn't have to be considered?
Oh, it has to be. Yes, but it has nothing to do with the phenomenon happening. Yes.
And for the reporter, on page 13. Okay, thank you. Do you think the density of particles will affect the result?
Yes, density affects viscosity, then it affects the result.
And do you think?
Oh, sorry, no. I mean, density affects viscosity, and viscosity does not affect boycott effect. Does not affect boycott effect, but affect settling rate.
I think the density affects the Reynolds number, which in terms helps correct the P&K theory. So it has to do more with the viscosity, more with the Reynolds number.
Okay, so do you think the length of the tube diameter will affect your result?
No.
No?
No.
Okay, do you think?
Can you repeat your question again?
The
roughness?
the length of the tube.
The
The diameter of the tube.
Oh, no.
Yeah, okay. And after the particles absorb water, the density will change, right? The density of particles will change.
No. density of the particle will not change.
Okay.
I'd like to make one correction. So I believe the diameter does affect because the PFA theory includes diameter at the bottom of the equation. So I think diameter is definitely one thing to consider.
So you change. I want to make some clarification. So you change the diameter, but not the whole container.
I think no matter what.
I'm asking reviewer.
What do you mean?
So you change the only diameter, not the
let's
container.
start.
Thank you.
Reviewer, 3 minutes to 2 minutes. Okay. We have 4 minutes to technical.
Okay, hello everyone. I'm Kimberly from 2020, and today I'm gonna review problem number 15, boycott effects. So for the problem statement, we think it has to be main focus on the phenomenon and investigate the parameters. So overview of the reporter for the observation measure method and tracker and total video for the theory, BNK theory, VSPNK, and the experiment, exactly. Okay, for the course, fluent English clear diagram and good explanation of BNK theory. For the cons, lack of clear experimental video. And for the overview of the opponent, he briefly talked about how the report utilized his theory to the experiments and also some inquiry to the reporter, then pros and cons. And for the pros, fluent English clear points of the question, but for the cons, he didn't mention the point of the density particles, and the opponents make the wrong points on the theory, which is BNK theory. And for the discussion, they discuss parameter. And first, opponent asks when to start recording the data, and reporter's opinion. He shows the PPT that is vertical sedimentation, and the second question, and the reporter answer, he take a certain view of the phenomenon. And for the third, opponent asks the consideration of amount of the force, and reporter answer injected ink, not the article. And our own opinion, we think that diameter will affect because the wall will also give the resistant force to the particle. And second, we think that the reporter should also talk about why there would be the comparison of the previous theory. And for the missing point, we think they didn't talk about the density of the particles, so we suggest the reporter to put it to the report. And second, also we suggest the reporter and the opponent can also be more focused on the phenomenal parts to have the deeper discussion about the phenomenal part, because the purpose statement have also mentioned about the explanation of phenomenon. And third, we suggest the reporter can take an overview of the phenomenon because it may have a different scopic view of it. And fourth, as for the opponents, we think they too focus on how the reporter do the experiments, but didn't mention about the main parameters of the results and the differences of the experiments. Okay, that's it. Thank you.
Okay.
Okay, so here's the concluding remark. PMK does not consider collision of the particle, so it is not complete, as we stated in the presentation, and has made various adjustments about it. The width of the rectangular chamber will affect the condensing area, thus affected the settling area. So I misunderstood the reviewer's question about diameter, and we think that PMK is a way to explain boycott effect. But there are more factors such as convection, sideways seepage, and instability. So there are many factors that cause this boycott effect, and the density of the particle will not change in experiment, as we said that we use silica sand throughout the experiment. And the syringe experiment shows that there exists sideways flow. So I think the opponent asked irrelevant questions. Okay, thank you.
Okay. Teresa, any question?
Maybe I have a question for the reporting.
Yes.
When you do the experiments, you said that you tilt it right after you put in the particles.
Yes.
So you did it very fast like that? Do you think it would make a difference if you do it very quickly or rather slowly?
Yes, I believe that there is some difference. Because, so when you do it slowly, it basically, and you put in the particles, it generates convections of the water flow. Or maybe, laminar or turbulent flow, yeah.
So you chose to do it quickly in order to have a more visible effect?
Can you please?
I was asking because you said you did it quickly, so I was wondering if you deliberately choose to do it quickly in order to have a more visible effect.
Oh. So I did it quickly, but I did not affect the flow inside the container.
Okay. So not so quickly, but
Yes.
not
Yes.
too quick.
Yes.
Thank you.
Teresa, any other question? No? Okay. Please write it. Go.
Thank you.
Ready? Okay, now give me the counter. 7, 7, 7, 7, 8. Now give me the opponent 8, 7, 8, 7, 7. Now give it a reviewer. 7, 7, 6, 7, 7. Okay. We finish this thing.